So, I wish everyone a good afternoon. My name is Daniel and I welcome you to today's online training for students. Today is the second part of our training series for students. Today we do the online training about Offering 6 for students in general. But today we get an introduction to the cross-section program, Rsection. So you will see today an introduction to the strength of materials. So calculating cross-section properties and also the cross-section classifications and so on, but more later on. My name is Daniel. I will be the presenter today, also with my colleague Bastian Eckermann. I am responsible here at Dlubal for the operative and strategic management here at Dlubal, and also for the sales and marketing. Today also Bastian is my second colleague. Maybe Bastian, could you introduce yourself, please?
Yes, hello. Thank you, Daniel. Hello from my side and good afternoon and welcome. And yes, my name is Bastian Ackermann, as Daniel already said, and I am working at Dlubal since 2017. I am involved in customer support, FAQs, chat, and also now into our new cross-section program, Rsection. So have fun with our webinar, and yes, then I pass on to Daniel.
Thank you very much, Bastian, for your introduction. So for those who are the first time here at GoToWebinar, some few words about GoToWebinar. So you have here the control panel. You can hide or show the control panel. If you have audio problems, then it's caused maybe by your audio settings. So you can adjust it here, select the right microphone and the right loudspeaker, and then you should listen us. And if you have any questions, don't hesitate to insert your questions here in the questions box. Me or Bastian will answer you these questions as fast as possible and as good as possible. So I will stop sharing my webcam, then you have a bigger overview about the topics today. Few words to the online training. The online training will be recorded. After the training, maybe next week, I guess, you will get the recording with a certificate, and we also publish the models to download and also the recording on our website and YouTube. So when some things are too fast for you, no worries, you can watch it afterwards. So our training series consists of 6 different topics. Today we have the second part, the introduction to the strength of materials. And what can you expect today? So first of all, you will get an introduction to Rsection. Rsection is our cross-section standalone program for the creation and calculation of user-defined and any different cross-section and profiles. You can calculate thin wall profiles and also massive profiles. This is a huge advantage that you need only one cross-section program, Rsection, in order to calculate various and different profiles and cross-sections. It doesn't matter if they are thin-walled cross-sections or if they are massive cross-sections. Yeah, then we do together a kind of introductory example. We will model together a thin-walled eye profile, and there we also see the calculated cross-section properties. We will also do a kind of cross-section classification and also apply some loads in order to see different results like bending, stresses, and so on. Then I will forward later on to Bastian. He will do 3 other examples also on thin walled profile, then also a massive cross-section according to the FE analysis, and then also a hybrid cross-section. Okay, so I will start with our section. So I jump to the program. Before we dive right into it, I would know from you, because I have also prepared some polls just in order to give an orientation for me and Bastian regarding your knowledge. So first of all, are you working with 2 monitors and screens? If yes, then I would adapt my pace to that. If not, then I would do it a little bit faster. Okay, most of you have already voted, so I will close the poll, share the results, and it's kind of 50-50. So I will do it, I guess, for everyone, I would say, so in a normal pace, that also the other guys who would like to model with me are, or I have the possibility to do that next to the second screen. Okay, perfect. So, and another poll I have also prepared is if you have already taken classes or experience in strength of materials. That would be also very interesting, because then it would be easier for you to understand the topics we do today. Okay, I will close the poll, share the results. And yeah, it's quite interesting. So most of you have already taken some classes regarding the strength of materials. I think this is also, especially in the beginning of the semesters when you study civil engineering, also mechanical engineering, you got an insight into the whole topic. So I think a lot of things will be clear for you. Okay, perfect. So at first, I would start with a general description of our standalone program, Rsection. Then I will give you an introduction to the whole user interface. And then I will say to you that you can model with me an example. Okay, so the first 5-10 minutes, you don't need to do anything, just watch and pay attention about our section. So Rsection, what is Rsection? It is a standalone program, and you can model and create various cross-sections and profiles. The cross-section can be thin-walled or massive. Why do we have Rsection? We have in RFEM, so our 3D FEA program, and cross-section library, and sometimes it can happen that the standard cross-section in the library aren't there, which you need for your calculation. So for example, this kind of cross-section is a typical example for that you don't have in the standard cross-section library in RFEM. So what you need to do is to create these cross-section in Rsection. This is also the reason why we have here Rsection. With Rsection, you can calculate all possible cross-section properties like sectional area, or also these kind of area moment of inertia, and also shear moments, statical moments, and so on. You can also get the centroid and so on. Moreover, you can also perform kind of cross-section classifications, and you can also consider effective cross-sections or effective widths of these thin-walled cross sections. And this is what Rsection can do. So cross-section properties, cross-section classifications, and last but not least, you can also perform stress analysis or stress proofs. Okay, so much to Rsection. Now I will explain you a little bit the user interface. So on the top, you find the menu bar. Similar to RFEM, you can create here the file menu, a new model. You can save it, you can print, you can create the printout report, you can import some DXF files. So when you're working, for example, with AutoCAD, you can import it. You can edit some objects, you can manipulate them, you can adjust them, edit them, and so on. You have also the possibility to set some views like the console, script manager, tables, and so on. Insert different and various kind of objects like no points, lines, parts, and so on. Also calculate tools. Tools is a quite important part here in Rsection, because we will use also here these two commands: create angled corner, create round corner. These are pretty important. And top to that, okay, the classical options, where you can also, when I go here to program options, and we are today an international group of students, you have always the possibility to change here the language you would like to have. So when you are from Spain or you are a Spanish speaker, you can change the language to Spanish, for example. And also you can change here the display properties. So when you want to work in a black background, you can change it here to load dark background. And I click on OK, and then you have here this black background or dark background. But I prefer the white background, so I will change it back to white background, and so on. Okay, so much to the menu bar. Then we have also the symbol bar. It's an fast access to the most important functions and commands, like the creation of lines or points or also new elements. Then we have here the navigator on the left side. The navigator is divided into 3 parts. So we have the data navigator, we have the display navigator, and when we have also results, then we have also the result navigator. So the first navigator is the data navigator. This navigator is a kind of organization of all model objects, model data, also internal forces, results, load cases and combinations. You can create per dialog different objects like a point. You go here to new point, or you can also edit them. It is structured in a kind of tree structure. So when I open here this arrow, all existing points appear there, and this makes it quite easy to see, okay, which kind of points in this case you have already modeled. Okay, so much to the data navigator. When I have, for example, some blue objects, like sometimes it happens that you have some blue objects, then it's because the objects, like material, for example, aren't assigned to any other objects. So much to that. And when you have a red, objects, then it is a false definition of this object, for example. But you will see it later, or maybe also at Bastian's examples. Okay, the next navigator is the display navigator. So similar to RFEM 6, I can hide or activate different display properties. For example, I would like to activate the numbering. So I see here the numbering of points, lines, and so on. I can hide the results. I can activate them, also points, and so on. And the last navigator is the result navigator. Here I can access the results graphically. So in this case, I want to show me the statistical moments, for example. I activate them by clicking on them, and I see it here at the working area. Here, the statistical moment. I have various options to control the display of these results. I can say, okay, type of display should be the kind of ISO bands, ISO lines, or yeah, just an easy distribution of this result. I can also say, okay, I will tilt this thing, without diagram, two colored, and so on. I have here various options regarding the display option of these results. Here in this upper part of the result navigator, I can also activate the unit stresses and so on. And then here we have also the tables. The tables are also very important because here we can also control and access all basic objects. So we have here an overview similar to the data navigator, as well as in the data navigator. We can also create and edit here in the tables different objects and also the load cases and so on. And we can see here the results of the analysis of this section. So we see here, for example, the sectional area, so square centimeter 105, then also some other cross-section properties like the banding, so the centroid relative to the 0 point. 0 point is here, and also kind of area moment of inertia and so on. Okay, so this was the I would say the rough introduction to Rsection and his user interface. Now I hope that you paid attention because I have prepared a poll for you. So please answer me that, and then we jump right into the first example. This poll is a multiple choice poll, so several answers can be correct. Okay, I will close the poll, show you the results, and yes, the most of you have chosen the right answers because all three answers are correct. So Rsection is suited for the creation of any thin-walled and massive cross-section. This is a huge advantage because you can model massive and thin-walled cross-sections. Then you can also calculate the cross-section properties and you can perform stress analysis. Okay, so let's jump right into it. For those who would like to model with me, now pay attention. So I create my first example. I click here on new model in the symbol bar. Alternatively, I can also click here on file and click here on new. So I will insert here the name, model name, thin walled eye profile. You can save it here somewhere. In my case, it's Beispiele. This is the German word for examples. And I refer here at first to the analysis method, thin-walled analysis. We have here in the base data two different analysis methods. The one is the finite element analysis and the other one is the thin-walled analysis. I do now here the thin-walled analysis. The difference between those two is that there is a difference in the calculation of the gross cross-sections. So with the finite element analysis, you calculate this according to the FEA theory. So this is mainly used for massive cross-sections like timber or concrete. and when you really would like to consider also cross-section classifications in the for steel profiles according to Eurocode 3, for example, then you should use this thin walled analysis. So here you consider an analysis for thin walled profiles and cross sections. So I will use this one. The option effective section I don't activate for the first. At first, we will activate this afterwards, and I will explain you also afterwards what does it mean when I have here activated this effective section. So then I click on OK. And I will do a very easy I profile. It's an IPE 300, but for easier things, I will neglect the radius. So we don't do a kind of roll section. We will do this later on. So at first, we create here a kind of new element. This element is also used for the cross classification later on. I will use here a new material. For those who don't have here a material, no problem. You can create here a new material. Just click here on create new material. And a new window appear with a kind of new material dialog. And there you have the possibility to open the material library, and you can search for the steel S355. Yeah, and then you have the possibility to choose one of these things. Yeah, I will decide here for this Eurocode, European Union S355, and I click on OK. But I have already done this before, so I click here on cancel, but you should click here on OK. Then this material will appear here. Okay, for our example, I will use here this S355. And now we do the first element of this I profile, and in this case, the bottom flank. So this has a length of, let me check, 150 millimeters and a thickness of 10.7 millimeters. And I will create it here at the 0 point local coordinate system. I click here on OK. And then we create the web. The web has a length of 289.3 millimeters and a thickness of 7.1 millimeters. And the angle in the work plane is 90 degrees. Now I change the orientation, so I can snap here the middle point of this element. I click on OK. And now I do the same for the upper flank. Again, here I have a length of 75 millimeters, thickness of 10.7 millimeters, and direction is here. And then I change again the orientation. And now I have here my cross section. So I have here my cross section, and yeah, the next thing is just calculating it, and then let's take a look together on the results. So for the calculation of this cross section, I go here to calculate, say calculate all, and I see here the cross section properties. First of all, the ordinates, the Y, Z ordinates. I can see them here as colored results. For me, it's interesting to see the cross-section properties. In this case, the sectional area. I have here this one, 51 square centimeter. Then I scroll a little bit down to the other results. I see here the centroid, so relative to the 0 point, the 0 point is here. And as you can see, okay, the y coordinate is 75 millimeters because we have here, this eye profile, which is symmetric in both directions. Okay, good. Yeah, and then we have also all other results like the statical moment. We have the elastic section module about the strong and the weak axis. This is important for the calculation, maybe for the bending capacity of different steel profiles. Then we have also here some information about shear. So the shear area. When you are interested in the shear center, and in this case, the centroid and the shear center are the same point or the same location, then the information about the shear center would appear here. But because the centroid is equal to the shear center, no further information are here. When they would be different, then we would see here different information about that. Then also information about the torsion, warping, plasticity is also interesting. So the plastic section modules about the y-axis, and also here this the plastic limiting bending moment about the y-axis and also the z-axis. And also important for you, the self-weight, so per meter, also pretty interesting to see it, and so on. So what can be also pretty interesting, the statical moments of that. This kind of display isn't so good, so I would put here this one, and maybe in order to have it similar like your hand calculation, I would activate here this tilting of result diagrams, and then you see it here like that. You see also here this shear distribution with the arrows. For a kind of better display of the results, you can also deactivate here the parts and also the elements, and then you see the results a little bit better. It's up to you how you would like to do that. And this was a very easy and general example. When you do some hand calculations by yourself for your study, or you have some examples, some easy examples, then you can always refer to our section. There you can enter and create this cross-section, and then you can compare the results of our section to your hand calculations if the cross-section properties are the same one as in your hand calculation. Okay, and then the next thing is that we will edit this cross-section a little bit. So I will deactivate the results here, and now you have to imagine that we do here this cross-section. So this upper part is like a T-profile, like a rolled T-profile, rolled cross-section. So we need here some a radius, and the bottom flank we would like to weld on the web. So we will here add some weldings, so some fillet weldings. So let's start with the cross classification, because now I want to consider cross-section classification for a steel profile according to the Eurocode 3. Eurocode 3 has 4 different cross-section classes, and now we can also do this classification with our section. therefore, I go here again to the base data and I activate here the option effective steel aluminum section. This allows me to perform a cross-section classification. So I will see which elements or C parts are responsible for that cross-section class. This is pretty interesting, and I will activate it. And the next thing is that we will show us here these sub panels. And as you can see here, these kind of sub panels are these C elements for doing this cross-section classification. Because you can do this also by hand, and our section considers this automatically. So this is important for performing this cross-section classification. So now we will add here these radius. So therefore we go here to options, sorry, not to options, to tools, and I will create here a round corner. So I go here to the round corner and I enter here a value of 50 millimeters. I choose here this line and this line, and then you can also see that the sub panels are fitted to the outer points of this radius. And let's do the same for the right side, and you can see how they change depending on the end of this radius, because this will affect also the cross-section classification. So right click, I will end this dialog. Now we will do here the next part. Here we will add an angled corner. So I go here again to tools, create angled corner. And now I choose here the corner type edge and angle. And I can insert here also a kind of formula. So the edge length should be 6 millimeters times the square root of 2, because we will consider a degree of 45 degrees. So I enter here SQRT for square root with braces, and in the braces I put here 2, and then I jump to the next box and the length is calculated automatically. And the degree is 45 degrees. Then I choose here both lines, this one and this one. And again, here you see that the sub panels are changed, and we do this on the right side too. Okay. So much to that. Now, in order to perform this cross-section classification, you will also need some internal forces, normal forces, bending moments, because then the cross-section classification is complete. So I go here to the data navigator, and you can see here I have the possibility to create load cases and also to add to the load cases some internal forces. Let's do that. So I will create 2 load cases. So I click here on right click, new load case. And the first load case should consider only normal forces. So I enter here only N for normal forces. I copy the whole thing, and here only bending moments. Then I jump to the next register, to the load combination, and there I create a load combination where all load cases are considered in one bigger load case, but only with these kind of factors. This is completely fine. And I click on OK. So now I go here to the chapter Internal Forces. And I add here for the first load case only normal forces, internal forces. So double click or right click on new internal forces. I enter here a value of minus 10 kilonewton. Why minus? Minus means that I consider compression forces. Positive normal forces are tension forces or tensile forces, and negative normal forces are compression forces. Okay, remember that, minus 10 kilonewton. Then I click on apply and next, and then I choose here the load case only M. Here I delete or I enter here a value of 0 at the normal forces, and the bending moment are 100 kilonewton meter. I click on OK. And then let's make a kind of check. So here we see the bending moments, 100 kilonewton meter. And here also the normal forces, minus 10 kilonewton. So this means compression forces. Okay, so much to that. Maybe I recall this internal forces again, because I want to explain you where they act or where they are attacking these loads. So when we apply here at normal forces minus 10 kilonewton, then they are in the centroid of this cross section. The same for the bending moments. When I activate here shear forces, then they are applied on the shear center. Okay, so maybe some of your exam tasks required some stress nodes at a specific location. And normally in our section, a lot of different nodes or points are given here. And these points are so-called stress points. Here you can see different values or different results for the stress for that location. When you want to have a result at a specific location, you can also add user-defined stress points. So this can be done here at stress points in the data navigator. Right click on that and say, okay, new stress point. In order to find our stress point very fast, I give them the point number 100, and I refer to my Y coordinate here to the middle point of this bottom flank, and the Z coordinate should be minus 100 millimeter. Why minus? Because we go against the global Z coordinate. Okay, I say okay. And where is our stress point? Here's our stress point number 100. Okay, perfect. So much to that. Now let's go to stresses. You have the possibility, when you want to consider kind of stress analysis, that you can adjust your stress configuration. Just click here with the right click or double click and go to edit, and then you can activate, for example, kind of various stress types, like this normal stress due to axial force, both tensile and compressive force. You can do this also, I don't know, for bending, for example, around or about the local y-axis. In standard cases, 3 stress types are already activated. This is this one, so the total normal stress, according this formula, also the limit shear stress and also the equivalent stresses according to Mises or for Mises. Okay, I will leave it here like that. I think, yeah, you can adjust it on your own needs. I click on OK. Yeah, and the only thing we have to do right now is just go to the menu bar, calculate, click here on calculate all, and then we going through the results. So first of all, I see here this thin walled analysis, and because we activated before in the base data also the option with the effective thin walled analysis, we see here also this other analysis. This normal thin walled analysis is suited for easy cross-section properties. So I go here also again to the thin walled analysis, and I can see here the section properties like this one and this thin walled analysis and the statical moments, also unit stresses, and also the normal stresses. And then you see here also the stress ratio according to the selected load cases and also load combination. This is also pretty interesting. Here the different stress type. And when we are interested for the stress ratio for our set stress point, I go here to stresses by stress point. I click here on our stress point, and now you see here also the stress ratio for our user-defined stress point. So much to the thin-walled analysis. Now let's jump to the effective thin-walled analysis. Now it becomes interesting because you can see here that we have here a sectional area of 52, and also that we have here a kind of empty, I would say empty part of this section, empty part, because now the program considers only according to the according to the cross-section classification only the effective section properties. So, and there we have a part which isn't effective, and this is also not considered in the whole calculation of the section properties. Okay, so now let's go here to the section classification. This is pretty important when you do here kind of cross-section classification according to Eurocode 3 with steel profiles. So here you see, okay, we have for this class 4. Why do we have class 4? Because every subpanels are these kind of things here. Every subpanel is analyzed by his classification or cross-section classes, and so we have here for the web these kind of class. So for class 1, but sorry for the flank, but for the web we have here other classes, in this case class 4. And normally it's like that the highest class is the final class for the cross-section class. So in this case class 4. And you can also take a closer look how the whole analysis is performed. So you have here this material coefficient. This is because of our material S355. Then you have here this different CT limits for class 1, 2, 3. And when this CT ratio of this web or of this subpanel is larger than lambda 3, for example, then you are automatically in class 4. And this class 4 is that class which will be also activated or considered as the highest class. And always the highest class is responsible for the correct cross-section class. Okay, so much to that. Then you have also this effective widths. So when I take a closer look to the subpanel 1, you see, okay, no ineffective width. But when I activate here this one, subpanel 2, I see here if ineffective width 19 millimeters, and this is this empty width or empty part of this cross section. Okay, and then also the stresses. You can see here the load case 1 with only normal forces. You can see here, okay, because we have very low normal forces, a very low stress ratio, and with bending, and then as combination. Okay, so much to that. I have prepared a poll for you that will summarize this a little bit, what we have done in this chapter. I will launch it. Okay, I will close this poll, share the results. So all 3 answers are correct. In order to carry out a cross-section classification, you need at first the internal forces, like bending moments or normal forces. Then you also need to activate the option in the base effective section. And on top of that, you have also to have subpanels in the part. So maybe what are subpanels? Subpanels are these kind of, maybe bones. I can say to them bones, or kind of elements here, this one. They are done automatically, and it's important to have elements. Element is, for example, this thing. So the right part of this flank, this is a kind of, maybe I will hide this. This thing, this is an element, and these elements consist of subpanels, and these subpanels are important for the cross-section classification. And the elements must be part of a part, and part is this surface, this one. Okay, good. So much to that. And now I would forward to Bastian.
Okay, thank you, Daniel. Then yes, okay. All right. Thank you, Daniel, for the introduction and the first example. Then I go on with the next example. By the way, there were no questions, so very good explained, I think, very detailed. Yes, and I go on with the next example that is also a thin-walled one. So it's an asymmetrical one, an standardized L section extended by 2 elements, one horizontally and one vertical. You will see this in a minute. So first thing I do is I am here in Rsection and open a new model by over the symbol bar, new model, and I give it the name thin-walled cross-section. Of course, the analysis, as you can see, according to the name, will be thin-walled analysis, because we are, as Daniel already explained, considering linear, thin-walled elements, which are linear and better to calculate with this analysis. We also activate the effective sections according to this norm and confirm with OK. Then I have my working plane here, and the first thing I do is I look up my materials. There are already some from the last example automatically saved. I can delete the concrete one because I don't need it, but it doesn't matter. I can also leave it. If I need another one or would like to change this one, I can just double click on it and select another one from the material library over this button. But I will stay with the S235 now, so I don't need this here. Then I go to sections and import a standardized L section as first step. So double click or right mouse button click and new section. And then, as well as with the materials, I go to the section library over this button and choose my standardized L profile over this button here. There I have all available L sections. I can filter them here on the left side according to region, manufacturer, and so on, or I can just search it in this bar down here. So it's an L. I give it, type it in, L space 200, 150, 12. And then I choose this one from the German annex. Yes, and I could also change the material here if I would have forgotten it, for example, but not necessary. So I confirm with OK. And then I'm back in this dialog box here, in this register section, location, rotation, mirroring. And there I can mirror this section, what I want to do about y-axis in this case, and I want to rotate about 90 degrees, like this. And then I choose the fixed point, which should be here in the center on the left side, on the left flange. And there I can see the local coordinates here on the left side. And when I want to insert it into my working plane in the global coordinate system, I can also choose the coordinates here, which are already correct, but I can show you by picking them in my working plane with this button here. So I click on that and choose this coordinate origin and then confirm with OK. So there's my L section, my L profile, and it's also possible to create this manually by drawing lines and or elements and angled corners like here, rounded corners, I mean, but also possible to choose the standardized ones directly. Now, as you can see, our section automatically recognizes elements here. Here you can see the arrows. There are already existing objects for each one. So here we have 2 elements. So our section already or recognizes 2 thin-walled elements here, and they are automatically assigned to subpanels. I also show you them here in the display navigator. I can activate the sub-panels here to show them. So as Daniel already mentioned, they are based on the norm which we chose in the general data in the beginning. So this one, for example, it means it's fixed here. So for this direction, it's fixed on the right side and free on the left side, and the other one vice versa. So then, of course, we also have a part, and these elements, I switch them, the subpanels off again. These elements are automatically or have to lay within a part. A part is necessary to have a final cross section. So Rsection automatically has recognized this one here. This is a part, means this looks like a surface in RFEM, if you know RFEM from RFEM 5 or RFEM 6. This is like a surface, so the whole section finally. Yes, okay, so as I mentioned, we want to extend this cross section here on the left side by one element horizontally and one vertically. So in order to do that, I have to create a normal geometry and divide this profile into single elements. I do this by right mouse button click onto the element, and then I choose section, and as I say, convert into normal geometry. So I have single elements now, and now I'm able to edit this cross section. Before we go on, we check this option here. This is deactivated auto split elements, which is important now because now I want to move away this rounded corner. I do this by deleting this point here. Point number 6, I delete it. And then you just see the elements which are not closed. So they are shown in red. Red means it's not a full cross section, not ready to calculate. If I switch the elements off in the display navigator, you can see it here. But that's all right for now because I want to go on and extend my cross section. So the next thing I do is I draw another element. I can do that by the data navigator here over new element, or by the symbol bar, new element, single element, and then I get this dialog box. I choose the input mode length and direction, and the length of the next element is 200 millimeters and thickness 12 millimeters. And now I could draw it, but I want to change the orientation or reverse it. And now it's correct. So at this point, I want to put the next element. And the next one, I can draw directly under it. So then the parameters are 400, a length of 400 millimeters and a thickness of 10 millimeters, so a bit thinner, and an angle of 90 degree. 90 degree and also reversed orientation. Now it's important to fix the element not under it here, because elements always have to share the same point, start or end point, in order to be connected. So this is the right point to choose now. I click it and Rsection automatically recognizes the sub-panels here, that they start in this point here. Now I can leave this this mode by clicking right mouse button, and then I switch the panels off again. Now I want to define some fillet welds here in the corner. So I do this by Tools, Create Angled Corners. So the corner type shall be edge and angle, and the length is 6 times square root of 2, so 8.5 again, and an angle of 45 degrees. And now I can just pick the corresponding lines here and on the other side. All right, now I leave that function with right mouse button click, and obviously I could create the whole section, the whole cross section now, because the boundary lines seem to be closed. And if that's the case, I can switch to my data navigator, and I can click on this part here. The part is red still because because the lines which are saved are not the correct ones. So I select the correct boundary lines now with this mouse button here. First I can clear the selected objects here, and now select all of them and confirm with OK. And again, OK. The boundary lines are not closed. OK, so I will take a look at this. Here is another one which is not used, or which is not necessary, so I can press Shift in order to deselect it. Shift, and now it should work. So the Shift key with the arrow to the top, then press OK, and OK again. Okay, they are still not closed. So I check again. This is all closed. Okay, I leave this function again, so I want to check it. Yes. Yeah.
I think there's also another line at the 0 local coordinate. Maybe when you, I believe that this was still activated when you selected all.
This one here.
Yeah, exactly.
Yeah, can be. Yes, thank you, Daniel. Okay, so I go back into this dialog box, select all boundary lines, clear this field, and now again, and now I press Shift, and yes, both are shown in black, so not selected, and now it should work. Okay, and okay. Yes, now my cross section is ready to calculate. And yes, you can see the subpanels here. this cross section. Now I can save it now and import it into RFEM or Rstab if I want to. But now we want to give it a load, so some internal forces. We do this with this button, load cases and combinations. So first load case is N for normal force, and the second load case is M, My, bending moment, and a load combination as well, both of them, N and M. I confirm this with OK. And now I have here in my data navigator internal forces. There I have my load cases, which are still empty. And under load case 1, I double click on internal forces. And I can also give more than one internal force, for example, certainly, but in this case only N. That is minus 50 kilonewton. And I confirm that with OK. And the bending moment as well, which is 20 kilonewton meter. Confirm this with OK. And now I can calculate either over the menu bar or over the symbol bar with this button, calculate all. Yes, now you see the results here, and in order to see them correctly, I switch off the display of the sub-panels. So, of course, again, I have my either my thin-walled analysis or effective thin-walled analysis, which is quite interesting now because we have different different single sub-panels and internal forces. So we want to do a cross-section classification, and first we see our ordinates here and the stresses. Yeah, let's go to the. But first of all, we have an asymmetrical cross-section here. So the shear center is not the same as the gravitation center. So you can see this here also under the thin-walled analysis section properties. If I scroll down here, you see the coordinates of the shear center here, for example. And then if I go to the stresses, sigma x total, for example, there I can see my effective cross-section now according to the bending moment, which is shown here in this bar. If I switch to the normal force first, for example, I see this field is empty here and also the whole part down here, because everything, the whole section gets pressure in this case, a normal force of minus 50 kilonewton pressure. So this part of the sub-panel down here will be buckling, and it's not carrying the normal force in this case. So it's not considered here within the effective cross section. And the same applies for this little part here on the left side. And for the bending moment, it's the same here in the upper part, but down here, of course, we have tension because of the bending moment, compression in the upper part, tension in the lower part, and that's why this part of the section is important for the bending moment. And for both of them, it's also this one. When we show or when we see the results here, we always have to watch the control panel on the right side, which is the legend for this. But if we say, okay, I want to see a graphic here or the values directly in the graphic, I can switch the type of display here from isobands to isolines, for example, which is not so good in this case, or I can switch it off and then I can see the values directly in the graphic. For example, for sigma x total like that, or for tau like this. Yes, and finally, I want to print this graphic into my documentation and then show you the documentation. So we go over the symbol bar and print graphics, or we go over this button and say print graphics to print out report. Then we have this window and can do some settings on the left side. But now we leave it like this and click Save and Show. We can give the name here, protocol thin-walled cross-section, T, thin-walled cross-section. And here we can activate or deactivate additional items on the left side and then confirm it with OK. Then we wait so our printout report can open. And now we have here the documentation of our section analysis. So first we see the model here, and then on the left side our printout report navigator, where we can switch into the chapter where we want to go, or we can scroll down. And here you see the symbol for graphic. There we can see our graphic, which we printed into our report. We can also edit the printout report here and deactivate items or activate additional ones. For now, this is okay so far, so I can cancel that and close the printout report. Now I save this cross-section because it's ready for RFEM, ready to calculate and to design it. So I say save as thin-walled cross-section. And before we go to the next example, we go to the poll and which is actually a statement that the analysis of thin-walled structures is suitable for the calculation of rolled or parametrized steel sections. I start this, and now you should see it and be able to choose right or wrong. Yes, everyone has voted, I think. I hope. Wait a few seconds. Okay, no. 45% only. Okay, then I close it now. Of course, this statement is right, so everyone who has voted correctly. Yes, the analysis of thin-walled cross-sections is there to calculate parametrized or rolled cross-sections. If there are no questions, I would go to the next example and close this one. So the next one will be an aluminum profile, which can be considered as a massive one. You will see it in a minute. We calculated with the finite element method because we have no regular thin-walled elements here. So mostly this can be concrete or timber cross sections, but it always relates to the whole size of the cross section. So if you consider the thin-walled analysis or the finite element analysis. So I will show you that, what I mean. I click on new model again, and aluminium profile is the name. You cannot model it along with me now, but because I have a DXF file, which you don't have, so you can just watch, but that's all right. So the analysis method is the finite element analysis, as I already said, and in this case we don't need a classification of sections. So I confirm this with OK, and then I import my DXF file over menu bar File, Import DXF, Alu Profile, open it. So it's, as you can see, you are not always required to draw your sections. You can also import it from DXF files, for example. After clicking import, you can see this dialog box and can choose the point and rotation, and if necessary also a coordinate system transformation. We leave it like this and confirm with OK. Confirm this also with OK, and then you see the file. So actually only lines. This is not ready, not finally a cross section. I have to define a part for that, as I mentioned before. You can also draw these lines by using the function here in the symbol bar, but it's also possible to import a DXF file easily. So the first thing I do is I click with the right mouse button on parts and define a new part over boundary lines. Now I'm in this dialog box, and of course that I forgot this, to create or define the new material, it should be aluminium, as I said, so not steel and not concrete. So I can also do this over here, over the dialog box new part, by the button new import new material from material library. I know exactly which material I want to have, so I search it in the bar down here, EN AW 6060, and then I have this one here, 6060 EP T66. Double click on it, and then I have my material here. Then I select the boundary lines with this button. I select all of them, and now I have to deselect the inner ones. So I press Shift again. I zoom a little bit so I can do it easier. I press Shift and deselect this one, this one, this one, and the last one. Okay, then I confirm with OK. And now again OK. And now you see the outline of the profile. The next step will be to define openings here. And before I say something else to the method, I do this. So I click on openings here to create them. Right mouse button click, new opening, and then I can directly choose the boundary lines for my first opening. It's this one. Deselect this one with Shift, and then I press OK, and OK again, and I have my opening here. Now I could do this again with 3 times, but I show you another function which is also possible. So I want to rotate this opening and copy it. So I select it first by clicking on it here. It's so that it's selected, and then I can use the function rotate selected objects in the symbol bar. Rotate copy. I activate create copy and say 3 times. Rotation angle is 90 degrees. And the point of rotation is already correct, but I make it sure over this button. Of course, the center. And then I confirm with OK again. And then you see all the openings. And finally, one in the middle. I have to do it manually. New opening again, select boundary lines, and be careful. Yes, like this. That looks good. Yes, then I can confirm with OK. Has to be closed, of course, all boundary lines. OK again. And then my cross section is ready. So now you can see if you would have said, okay, I want to have the thin-walled analysis with a cross-section classification of elements, it's quite hard to do that because I have a quite irregular cross-section here. I could say this could be an element here, but the next ones would be quite hard to define. So this makes sense to, or this example is very useful to use the finite element calculation as a method here. So yes, finally I will give them, or will give it some internal forces, one normal force and another load case with torsion, and also load combination, combined both of them. to make it complete. And as you know, over the data navigator, internal forces, a normal force of -10 kilonewton and a torsional moment of 0.3 kilonewton meter. And then I calculate all. Yes, now I have my results here. Again, as you know already, the ordinates and unit stresses and stresses sigma x in total. Of course, nothing for torsion, but for n, here, according to the control panel, -6 everywhere. And yeah, if we can see the combination here, the same, and for tau, the shear force, this one. The equivalent stress I want to import as a graphic into the printout report over this button again. Save and show. Name is protocol aluminium profile. Confirm this with OK, and then I have my documentation. Yes, again here my graphic and all other chapters on the left side. I close this again, and now it's ready to calculate as well for RFEM or R-stab. If I save it, I have to save the file with results, of course. Okay. And yes, I can replace this. All right, before we come to the last example, we go to the poll again. So again, a statement. The analysis according to the FE method is suitable for massive cross-sections such as concrete or timber. I started, right or wrong again. Okay. Almost 50% have voted. Okay, I close it. Everybody who has voted right, so 100% correct. Yeah, there you can see it. So of course it's correct. The finite element method is according to, or we have it in order to calculate massive profiles for concrete or timber, because most of them are not, or actually no cross section of concrete or timber can be considered as a thin-walled one, because most of the time we have alu profiles or steel profiles as thin-walled cross sections. But in this case, it was a bit confusing maybe, because we have an aluminium profile, but which was considered as a massive profile. But actually it's only because it was so irregular that we have not only linear elements which we can classify. That's actually the reason. So then I would go on with the last example. Yes, okay. I close this. And yeah, the last example, or I can say it first. So it will be a composite beam. It's also possible in Rsection to model cross sections as hybrid ones with different materials, and also save them and import them into Airfm or Airstab in order to get internal forces here. Because as you know, the stiffness of different materials is different, and then the internal forces are, or this has an influence onto the internal forces. So we will look at a concrete slab 1 meter wide and 20 centimeter high, supported by an HEB 400. So I open a new model and call it composite cross section, and we take the finite element analysis, no effective sections, and confirm with OK. So now I draw manually a section for concrete first. I do this with new line, and it shall be 1 meter wide. In order to have it in the center, I start here at minus 500 millimeters, go to plus 500 millimeters, then up to minus 200, and back again. And I leave the function with right mouse button click 2 times. And actually, this is the outline of my concrete part. So I can define the part here easily over right mouse button click, new part, boundary lines. Of course, the material, it's already there. If not, I can choose it, as you know, over the library. We take this one, C4050, and choose the boundary lines over the button. All of them confirm with OK, and again OK, and that's it for the concrete part. For the steel part, or the HEB 400, I go over sections, new section, and choose from the library the parameterized H-beam over this button. I go to this one, Euronorm, and take the HEB 400 here. Material is S235, that's all right, and I can confirm this with OK. Here I choose my fix point first, so it's this one here on the top in the middle, and then I can choose it here where I want to have it, where I want to place it over this button. It was already the correct one, but like that you can see it. So then I can confirm this with OK. And now it's ready. The cross-section is ready to import or ready to save and import in RFEM or Rstab. In order to control it, I can set or give it a bending moment, my, confirm with OK, and give it a bending moment of 100 kilonewton meter, confirm with OK, calculate all, and get my results here. Sigma X total, I have compression in the upper part, in the concrete part for a positive bending moment, and tension in the lower part of the cross section, which is correct. Yes, so then I can save it. Save as with results. Composite cross section. And then I open RFEM in order to make it complete, to show you a quick example, an easy example as a cantilever here. So I open RFEM and open a new model. Composite beam. Confirm with OK. And then I can draw my member over the button New Single Member. Then I have this dialog box, New Member, Main and Section tab. I go to the Section tab and I have to create a new cross section here. So I choose the Library button. So far everything is clear. Maybe if you are using RFEM, then I choose the button on the right side from Rsection, this button here. And then I can choose Rsection files wherever I have saved it. So this one was the composite cross section, which I wanted to show you. Of course, I can also import every other Rsection profile that I have saved. Composite cross section, open it, and then I get this dialog box here, edit section. There you can see this option here, hybrid, which is already activated. And if it's activated, it has to be, because there are different materials. You go to the tab hybrid, and there you see the different material assignments. So now we have to check it and change it. The part number 2 is not concrete, but steel. So we change this into S235. If it's not there, we can also define it over the material library, of course. So S235 in yellow, and there we see it. That's correct. Part number 1 is already concrete, and then we can confirm this with OK. Now we defined our cross section here. Again, here you can see it. Then we can confirm this dialog box for new member also, and then we can draw our member. As I said, only a single easy cantilever here in order to make it complete with a fixed support. So like that. And then you can load it and get internal forces for this, where the different materials are considered because of the different stiffnesses. That's it from my side. If you don't have any questions, there is a question. Why is not the M1, M2 materials already considered when imported the composite section? Yeah, good question. You mean one second here, edit. I think you mean here that it's considered correctly here. Well, to be honest, I have no answer to this now, but I think it's always good to check what you are doing. I think most of the time you have not many more than 2 different materials in one section, so it's always good to check this, and yeah. But I can make a note here to get to maybe have this as a new required feature that we can recognize it directly, if that's possible. I cannot confirm it right now. Yeah. Why you need to? Okay. I think the question is answered so far. Or Daniel, can you, if you have anything
Yes.
for that?
Yeah, I guess the question is answered. Maybe we can get back on that when you clarified it with our development team.
Yeah.
We could add features.
Okay.
So
Yeah, if that's everything, then from my side, this is done, and I hope you had interesting input and useful input for yourself and enjoyed the webinar. And yeah, if there are no questions left, I would pass on to Daniel again.
Okay, perfect. Bastian, thank you very much for your part of this training. Also from my side, there's nothing else to say. A few words maybe to our website where you can also find useful information. Therefore, I take over the control. So here our website, and especially for you students, you have the possibility to go here to the education part or area of our website, and here you find other useful online training or online courses about RFM 6 for beginners. Also, we have a kind of knowledge platform where we offer different information regarding the first steps with RFM, other videos, also technical articles in our knowledge base, and so on. When you are writing your master or bachelor thesis, then I can recommend you to submit your thesis when it's also about our software. You are using our software. Why? You will get a gift from us. You will get an Amazon voucher, and also after your study, we allow you to use for the next or for the first 6 months after your graduation to use our structural analysis program. So I can only recommend it to you when writing a thesis with with the help of our software, to let us know and to submit your thesis. So with these words, I want to say goodbye and also to thank you for your attention. I hope you got some nice insights to the whole strength of materials theory. We modeled thin-walled structures or thin-walled profiles, did cross-section classifications, and also calculate the cross-section properties. On top of that, also of a massive cross-section. So thank you very much, and I hope that we see us next week, where you see an introduction to the whole FVA theory with RFM 6. So wishing you a nice day and stay healthy, and see you the next time. Bye.